In this video, we're going to be looking at the relationship between non-standard and standard delta G. As a reminder, this what looks like a degree symbol associated with this delta G. This notation is used to indicate that this is standard delta G, meaning that it meets the criteria for being under standard conditions. Standard conditions are when the temperature is 25 degrees C, when the pressure of all of the gases in the system are 1 atmosphere, and all solutions have a concentration of 1 molar. So in order for a delta G to qualify as being a standard delta G, it has to meet all three of these conditions, unless one of them doesn't apply. So if there are no gases, then of course this does not apply. If a system violates any one of these standard conditions, like maybe the temperature is too low or too high, or maybe the temperature and pressure are just right, but one of the concentrations is off, then we refer to it as a non-standard delta G. And again, non-standard delta G comes from violating any one of these standard conditions. It doesn't have to be violating all of them. Most of the time when we're collecting data, the data that we're collecting is not falling under standard conditions. It's pretty hard to meet a couple of the standard condition requirements. And so in that situation, most of the time when we're collecting data and using it to calculate delta G, it's a standard delta G. There is a relationship between standard and non-standard delta G. This particular equation right here, non-standard delta G is equal to standard delta G plus RT ln Q. There's a lot of terms in this equation, so we're going to go through them quickly and just kind of talk about what each one represents. Of course, this is our non-standard delta G, and then we have our standard delta G. Standard delta G, we're usually going to calculate that mathematically using delta G standard equals delta H standard minus T delta S standard. So that's an equation that we used or learned a little while ago. Or we could also calculate delta G standard using Hess's law, taking the delta G of formation of our products and then subtracting reactants, products minus reactants. So we could calculate delta G standard either one of these ways using either one of these methods and apply that to this equation. R is the ideal gas constant. However, it is with different units. So we normally know the ideal gas constant as being 0.08206 with the units liters, atmospheres per mole Kelvin. We can do a unit conversion on R, which puts it into units of kilojoules or joules, which makes it more useful in this particular type of equation. When we do that unit conversion, the numerical value of R changes along with its units. So in this equation, we're using this version of R, 8.3145 moles per Kelvin. T, of course, is temperature, and in this equation, the temperature needs to be in units of Kelvin so that it's consistent with R. And then last but not least, we have Q, the reaction quotient. Products over reactants, calculated the same way that we would calculate an equilibrium constant, K. So there's a lot of stuff involved in using this particular equation. Let's take a look at an example of how we could use it. Here we have a reaction that's in equilibrium. H2 plus O2 makes H2O. We want to know if this reaction is spontaneous or not under these conditions, and we've got some pressures, we've got a temperature, and we have some delta G values over here. Because these pressures are not equal to 1 atmosphere, we know that this is a non-standard reaction, or the conditions are non-standard, which means that when we're trying to figure out if the reaction is spontaneous, which means that we're trying to figure out not necessarily the value of delta G, but just simply the sign of delta G. Is it a positive number or is it a negative number? Because we have non-standard conditions, that means that we cannot use the easy ways of calculating delta G. For example, delta G equals delta H minus T delta S, or Hess's law, delta G equals products minus reactants. Those are not allowed. those will absolutely calculate the standard delta G, but they will not calculate the actual delta G for this non-standard reaction. So in this situation, we are going to have to use this equation, delta G non-standard equals delta G standard plus RT natural log of Q. One of the kind of tedious things about using this equation is that there are a couple other things that we have to solve prior to actually solving this equation. So we've got to calculate our standard delta G. We also have to calculate Q. And then once we get those figured out, we can plug them into this equation along with R and T and get our answer. Let's start by calculating our delta G standard. The delta G standard, because we have delta G of formation values in this problem, the easiest way for us to calculate delta G standard is going to be with using Hess's law. This is not going to be a very straightforward way to calculate, because in order to use this equation, we would have to use Hess's law to get delta H and Hess's law to get delta S and then put it all together. So that's pretty tedious. So we're just going to use Hess's law with the delta G values to get this to get the standard delta G. So this is going to be products, which in this case is, our product is H2O. Remember that we need to multiply each one of these delta G's by the stoichiometric coefficient. So 2 times the delta G for H2O, and then we're going to subtract from that our reactants. We have 2 times delta 2 times delta G for H2, and then our other reactant, 1 times the delta G for O2. The delta G values are right here. We're just going to plug those in. 2 times negative 228 kilojoules per mole minus 2 times 0 plus 1 times 0. This works out to be negative 456 kilojoules per mole. So there is our delta G standard, and I'm going to take this number right here and I'm going to start filling this equation in. So negative 456 kilojoules per mole. Now our next term in this equation, R, which is the ideal gas constant with slightly different units, 8.3145 joules per mole Kelvin, times the temperature in this equation, 25 degrees C. If we convert that by adding 273, we get 298 Kelvin. 298 Kelvin. I don't have a ton of room here. And we also need to add into this the natural log of whatever Q is. So that's our next step, is to calculate Q. Q, if you recall, is calculated the same way that we would calculate an equilibrium constant. So it is going to be, this is going to be products over reactants in the fraction form, each one raised to their stoichiometric coefficients. The data that we have to calculate Q is a whole bunch of pressures. And we have the pressures of all of these gases. So we're going to, on the top, we're going to have the pressure of the H2O gas, and that is going to be squared. And again, that's because it's our product. Products go on top. And then our reactants down on the bottom, we're going to have the pressure of the H2 gas, which is going to be squared, and the pressure of the O2 gas. And this pressure is not squared because the stoichiometric coefficient for that is just 1. We can plug the pressures into this Q. So the pressure of water is 7.01, and we're going to square it. And then the pressure of the H2, that's 1.35, and it's also going to get squared. And then the pressure of the O2, 5.64. And this works out to be 4.8 when we do the math on the whole thing. So 4.8 is our value of Q, and that number we're going to stick right up in here. Can kind of barely have enough room for this, going to move this Q calculation down out of the way. So let's work on the algebra of solving this particular equation. So what I'm going to do just in the first step to kind of try to condense this down a little bit, we have the 456 kilojoules per mole. And what I'm going to do is just work out all of the math on this side of the equation. So I'm going to begin by taking the natural log of 4.8. And then I'm going to multiply that by 298. And I'm also going to multiply by 8.3145. And that is going to get me 3,887. And if we pay attention to our units here, the Kelvin unit will cancel, so we end with units of joules per mole. Now all we have to do is add these two terms together, but before we get too excited about that, we notice that we have a little bit of unit inconsistency. That's always going to be the case here. You have a choice. You can either convert this into joules, or you convert the other one into kilojoules. It's completely up to you which one you would rather do. I'm going to convert my joules into kilojoules by dividing by 1,000. So instead of 3,887, it's going to be 3.887 kilojoules per mole. And this works out to be negative 456 plus 3.887, approximately negative 452 kilojoules per mole. So much work that we did here. All we really needed to know was the sign of delta G. That's not always going to be the case. A lot of times you're going to be needed to actually do the calculation of the numerical value of delta G. But since we can now see that delta G is a negative number, we know that this reaction is spontaneous. I'm going to fill this in up here. This is spontaneous. And the reason that we know it's spontaneous is because we have negative delta G, which we calculated right here.